All right, today we're going to talk about applications of exponential functions. This should actually say exponential, not log. And we're going to start with the compound interest formula. So just to remind you, if interest is compounded n times per year, the amount is equal to the principal times 1 plus the interest rate, annual interest rate, divided by n, raised to the n times t. We had this in the beginning of the chapter, but now this time we're going to either be solving for, well, usually we'll be solving for t rather than n. For continuous compounding, a is equal to the principal times e to the rt. For both of these, time is measured in years, and the interest rate is converted to a decimal. So our first example says you've deposited a certain amount of money. They don't always tell us how much. That's P, into an account that pays 6.75, so 0.0675 as a decimal, percent interest, compounded continuously, so I'm using this formula. How long will it take your money to double? So, and then how long to triple? The reason it doesn't matter how much money we start out with, whether you're investing $1 or $1 million, we're just talking about doubling the money. So for the first equation, if I invest P dollars to begin with, then I'm looking for the amount to be 2 times P. And then we're using the E to the R T equation. And the first step for solving this exponential equation, isolating this E term, is to divide both sides by P. So it doesn't matter if P was $1 or $1 million. When you divide double P by P, you're going to get 2 every single time. So 2 equals E to the 0.0675T. We learned in a previous section that we should be taking the natural log of both sides so that we can cancel out that exponential base and free up, I didn't mean to cancel the exponent. The natural log cancels out the base E, and that frees up this exponent. So the natural log of 2 equals 0.0675t, and we can solve for t by dividing. So the natural log of 2 divided by 0.0675, rounded to 3 places, is 10.269. Always label, this is years, so about 10 years to double your money. And then the question also said to triple, so again, it would be if you invest P dollars, you're looking for your equation to equal 3P, same interest rate. I'm going to divide by P. It's okay with me if you set this up to begin with as triple is going to be 3 equals E to the RT. That's fine. And then the math is going to be the same, so I'm not going to show every step here. Natural log both sides, which makes this natural log of 3 equals 0.0675t, and solve for t. So tripling our money, just need to change this to a 3. Tripling our money is 16.276. And I'll call that years. So those are our approximations. We have other exponential models that are important to look at, common exponential models. So we have exponential growth and exponential decay. And take a look at these two equations. The equations are almost the same. The only difference, this should have an x in it. The only difference is that this says bx and this says negative bx. Both of them say b is greater than 0, but that's because the negative is built into this equation. So that's kind of a strange notation there. Comparing to these graphs, exponential growth is the first graph. We say something grows exponentially, we mean as x increases, f of x increases, and that rate is getting faster and faster and faster. The next graph is exponential decay. As x increases, f of x decreases, again at a faster and faster rate. And then the third that you might not be as familiar with is called logistic growth. So we look at populations and we say, oh, the population has this exponential growth, but those exponential growth models, at some point, they almost always have this right here. This is the point of inflection where the concavity is changing. But a lot of populations have sort of a cap on them. Populations can't just grow without bound forever and ever. There's got to be some sort of leveling out. Some parts of the species will pass away as others are being born. So, anyway, there's this point of inflection here. And the point of inflection is always the fastest rate of change. It's where we're switching from concave up to concave down. So think about this. These slopes are getting steeper and steeper and steeper and steeper. This is the largest positive slope that will exist right here, largest positive tangent slope, and then they start leveling out to zero again. This is our logistic growth model, where it grows exponentially for a while and then starts flattening out. All right, so the revenues in billions of dollars for Amazon.com from 2011 to 2016 is modeled by this. Again, there should be a T here. I think it printed strangely to this program, where T equals 11 represents 2011. According to this model, when will the revenues reach 300 billion? So this would be a calculator problem. Well, we could solve it either way. Let's see. 300 equals 5.3 e to the 0.201t. If I could solve this by graphing, right? We'll look at that in a minute. But I could also, possibly just as fast, solve this almost by hand, I guess, and then use the calculator to get the final thing, just like we did for our for these problems back here. I could have also graphed when is natural log of 2 equal to this, found an intersection point. If I do that, it would be the natural log of 300 divided by 5.3 equals the natural log of e to the 0.201t. So solving for t, it's going to be the natural log of 300 over 5.3 divided by 0.201. That's the exact answer for t. We might want a calculator to approximate it. The reason I show this is maybe the multiple choice answers will be in this form, and then it wouldn't be a calculator problem instead of calculating it out. So let's just see what that comes out to. All right, so we have the natural log of 300 divided by 5.3, close parentheses, that's all in the natural log. That answer will get divided by 0.201. And we'll round this to t is about equal to 20 point, this would round to 0.80 years. No, sorry, not years. This equates to what year we're in. Get my little eraser out. 11 was 2011. So if t is about this, that is saying, let me see what the question, how it's phrased. When will the revenues? So this is years since 2000, I guess. So it would be, so I would just say during 2020. Now, the interesting thing is that you can look up, like this is an actual model that predicts that models the actual Amazon revenues over that time. So I did double check this and kind of look, and this is an accurate model. You can go back and check 2020. And I don't remember because 2020 was pandemic, right? So I don't remember if the revenue shot up then or not, because we were all home ordering things. So anyway, the model is accurate though, which I thought was interesting. An exponential model changes by the same percent each year. This is a question I saw pop up a few times in AP Classroom. What is the annual percent increase for Amazon's revenue model? So here's the way percent increase works. You have y equals a times b to the t, right? And this b value, if we have a percent increase, is 1 point something. So whatever that extra decimal point is, that's your percent increase. Like if it's 1.05, 5% increase. So ours is not in terms of B. Ours is y equals 5.3 e to the 0.201 t. So the b value that we have is e to the 0.201. So let's see what that comes out to. Okay, so that is 1.223-ish to the t value. So for us, for Amazon, for our problem, it's about a 22 point, maybe I want to take this further, 22.262% increase. All right. If this said what's the percent decrease, like if this comes out to 0.9 something, you would do 1 minus that. It was like a 10% decrease or loss. It just depends on the model. In a research experiment, a population of fruit flies is increasing according to the law of exponential growth. So remember, our exponential growth model is back up here, a e to the bx. I'm going to write that down. Y equals a times e to the bx. After 2 days, there are 100 flies, so the point 2, 100 exists on this graph. After 4 days, there are 300 flies, so that point exists on the graph. How many flies will be there after 5 days? All right, we can't just do a slope because we know that exponential equations grow, the y values grow in proportion to each other. So let's start setting up what we know. The 2 is an x value and the 100 is a y. Same here. So let's set up a couple of equations. We have 100 equals, excuse me, a times e to the b times 2. So I'm going to write 2b. And the other equation is 300 equals a times e to the 4b. 4 is x. Now these two equations both have two unknowns, but we can solve each equation for a by dividing by e to the 2b or dividing by e to the 4b. If both of these equations are equal to a, then I can set them equal to each other. 100 over e to the 2b has to equal 300 over e to the 4b. This is now a rational equation of sorts that I can solve. I can cross multiply, right? So I can say 100 e to the 4b equals 300 e to the 2b. Bring this work up here. I would like to get the e's on the same side, so let's see. I'm going to make it e to the 4b over e to the 2b equals 300 divided by 100. So I just said divide the 100 to the right side, divide the e to the 2b to the left side. Well, we have exponent rules here. 4b minus 2b is e to the 2b. 300 divided by 100 is 3. And this is a nice little equation. I can natural log both sides. 2b equals natural log of 3. B is natural log of 3 over 2. Now, I don't want to find a decimal for this yet. I'm just going to leave it in its exact form and then carry on. Now that I know B, I can go back and find A. So you have two equations to figure out A. Pick your favorite. I'm going to pick the one with smaller numbers. 100 divided by e to the 2 times natural log of 3 over 2 equals A. These 2's cancel out. 100 over e to the natural log of 3. E to the natural log of 3 is 3. Excuse me. So we have A and we have B. And now we can go back and figure out when we plug in 5, what's the model going to spit out? So here's the model. Y is equal to 100 over 3 times e to the, keep this b value, natural log of 3 over 2, times what is x? X is 5. All right. Now at this point, I'm going to use my calculator, and I just need to type this in carefully. So we have 100 over 3 times e to the Maybe we'll put 5 first. 5 natural log of 3, close parentheses, divided by 2. It's probably the best way to type it. 519.615. Now we are talking about fruit flies, and I know the initial population here has a fraction of a fly in it, but we're just going to say about 520 flies. I like to always show the decimal, and if we're talking about people, animals, whatever, things that need to be whole numbers, then I round them up, but I keep both. Okay. To estimate the age of dead organic material, scientists use the carbon dating model, R equals 1 over 10 to the 12 times e to the negative t over 8,223. Okay. The ratio of carbon 14 to carbon 12 in a newly discovered fossil is this. Estimate the age of the fossil. So we're trying to find t. We have a value to set r equal to. 1 over 10 to the 13th equals 1 over 10 to the 12th times e to the negative t over 8,223. Isolate the t by multiplying by 10 to the 12th over 1. So this simplifies a lot. This is 1/10 equals e to the negative t over 8,223. Natural log both sides. The natural log of 1/10 equals negative t over 8,223. Multiply by negative 8,223. And that should leave us with t. And let's see what that is. Negative 8,223 times the natural log of 1/10. That's pretty old, right? We're talking about a fossil here. So t is about 18,934.157 years. That's the age of the fossil. That's kind of cool. Okay, and then our last model. So far we've done exponential growth. This was exponential decay. You had a negative exponent here. On a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. The spread of the virus is modeled by this. This is that logistic growth equation for t values greater than or equal to 0, where y is the total number of students infected after t days. So 2 parts to this. How many students are infected after 5 days? Now that's just y of 5. I could have given this to you in the beginning of our chapter. We're just plugging in 5 for t. It's e to the negative 0.8 times 5. So 5,000 divided by, put parentheses around that denominator, e to the negative 0.8 times 5, close parentheses around the denominator. So how many students are infected? I'm going to write the decimal, and then I'm going to round it to the nearest student. So 0.019, but we'll call that about 54 students infected. All right. The college will cancel classes if 40% or more of the students are infected. After how many days would classes be canceled according to the model? So we could find, so remember, y is the number of students infected. We could find 40% of 5,000 to see what to set our equation equal to. 2,000. So 2,000 is equal to 5,000 over this denominator. If I want to start solving for t, I need to isolate the e expression, and it has to be out of the denominator. So multiply the 2,000 without distributing. Multiply the denominator over to the 2,000 side without distributing 2,000. And be careful how you write this. I just wrote 0.08, and that was wrong. negative 0.8t. The reason I say don't distribute is because you're going to turn around and divide 2,000 to the other side. Five over 2, or 2.5. All right, and then we subtract 1. Divide by 4,999. E to the negative 0.8t is equal to this. Let's just see what this is. 5 over 2 minus 1 divided by 4,999. It's not going to be pretty. So you can do that on your calculator screen if you want, but just leave it like this. Don't round it to 3 times 10 to the negative 4th. Leave it like that. I'm going to natural log both sides. So negative 0.8t is equal to the natural log of all of this. I don't want to have this fraction in here, so let's see. 5 over 2 minus 2 over 2 is 3 over 2. Oh, my pen stopped working. Just a minute. It runs out of charge. Okay, so 3 over 2 over 4,099. So we can put all this down here together. Whatever. And then divide by negative 0.8. So how do I do that on my calculator? I already have the number inside the logarithm, so I can say natural log of that. Divide that by negative 0.8. So I get t is about 10.139. And what was t? How many days? So we wouldn't round this to the nearest day. I would say after about that many days. Because I don't know, are they going to cancel it on the 10th day when they're just short of 40%? Or would it be the 11th day when they're a little over 40%? So I would just say this. All right, that's it for models. So you can see I'm still using all of my equation solving. I did not use the graphing feature for any of these, although you could. And it's just about fitting the window. And not all of these had a nice specified domain for us to fit the window easily. So I would just solve. I think it's just as fast. All right, that's it for today.